Welcome back, and I've got another fun and unusual experiment for you today. What we're going to be looking at is power in electrical circuits. And then all you do is just put your drink down on the bar and you leave it alone. I'm not sure you expected that to happen, and neither did I. So let's try and explain what's happening. Electric fields apply forces to charges. Why does putting two transparent things on top of each other do something so strange when you turn it through 90 degrees? So we've got Bjork with us today. You'll notice that Pippin the pony isn't here. He's off on one of his missions, and more of that at the end of the video. So what are we going to play with? Well, I've got two reels of wire here. It's bare wire and it's made of exactly the same metal, Constantan. However, one of the wires is thick and one of the wires is much thinner. You can see from the close-up picture which one's the thick one and which one's the thin one. And we're going to wire these up in different ways and look what happens when we connect them to an electrical power supply. Now, I was shown this experiment many years ago and it's really rather fun, so I thought you might like to see it as well. I'm going to take a piece of each of the wire. So let's take a piece of the thin one and let's take a piece of the thicker one. And what we're going to do is we're going to wire these up so they're in series to begin with and then in parallel. But to make it a fair test, of course, we've got to make sure that our two lengths of wire are exactly the same. So I'll trim them both down. And in a minute, what we'll do is we'll wire them in series and pass some current through them, and then wire them in parallel and see what happens when we pass some current through them. Right, I put some crocodile clips on the end of each bit of wire. So here's the thick one and here's the thin one, connected to the positive and the negative of the power supply. So all that remains for me to do is just to join these two crocodile clips together. And when I've done that, we'll have a series circuit and we'll pass some current through it and see what happens. So we've got our series circuit now coming through the thick wire and then through the thin wire. So let's turn on the power supply and slowly turn up the current and see what happens. So you've got to remember they're in series and, oh, this is beginning to burn the paper. And the very thin one gets very, very hot and begins to smoke. And the thick one doesn't appear on camera to do anything at all. So what we've got to do now is rewire the circuit in parallel. So I hope you can see now that I've got them in parallel. I've got this link on this side and the other link on the other side, and the negative here and the positive there. So we've got the thick one closest to me and the thinnest one closest to you. Remember that the thin one was the one that heated up the most. When they're in parallel, it doesn't matter which way round they are because they've both got the same voltage across them. So what we'll do now is turn up the power on the power supply and let's see what happens. So I've moved the camera a little bit closer. So let's turn on the power supply, pass the current through these wires and watch which one gets hot first. So there we go. Have a look at this one. That's the thick one this time getting really hot. And last time it was the thin one. So this is going to need some explaining. By the way, to prove that I wasn't cheating with this parallel circuit and that I had the bottom one disconnected, we'll turn up the voltage again, watch the thick one get hot, and I'll keep turning up the voltage, and after a while the hot one melts, and of course so does the thin one as well if you give it long enough. But you'll remember it was the thick one that got hottest first. So, time for an explanation of this lovely and slightly counterintuitive experiment. I've made the wire green now so you can see it slightly better. We wired them in series first, and the main thing you need to know about series circuits is that the current through both must be the same because they're in series. But the power dissipated is equal to their resistance times by the square of the current through them. Well, if they've got the same current, then the square of the current on both is the same, but the thinner one has the higher resistance. So this one will dissipate more energy per second because the I squared R is bigger. Right, you ready for the explanation of them in parallel? Now, when we put them in parallel, we saw the opposite happen. They're in parallel, so they've got the same voltage across them, but the bottom one will have less current than the top one. Now, I hear you say, but this one has more resistance because the current's lower, indeed. But remember, the power dissipated depends upon the resistance multiplied by the current squared. So if this one has a lower resistance, then the current will be higher, and the current squared will be much higher in this one than that one. So the power dissipated in the thicker one in parallel is more. So the thicker one will heat up first. So let's have a quick application of this. Now, in something like a toaster, you want it to get hot, so you make sure that the wires don't have too high a resistance, but they do have a lot of current. So if you square the current, I squared R, you'll get a lot of heating. But the opposite's true if you want to get electrical energy from one place to another without losing much. And so with the national grid, when we transfer electricity from power stations to towns, we don't want to lose energy. Well, the cables have resistance, but if the loss in the cables, the warming effect, I suppose, is I squared R, if we can make the I as low as possible, we won't dissipate much energy. And that's why we carry electrical energy on the national grid at very high voltages indeed. And perhaps power lines will be a topic for another video. So I hope you enjoyed that video and learnt a little bit about power dissipated in electrical circuits and the formula that is I squared R. Anyway, we'll have another video soon, and I look forward to seeing you then.